Gao Yang. So this is my presentation on my term paper on the topic of edge computing networks. So first, an introduction of what edge computing is. Essentially, is computation that is being performed on the network edge and downstream of the centralized cloud services and on top of the IoT devices. It allows for localized processing, thereby minimizing dependence on the centralized server. Its rise is in tandem with the emergence of IoT, where IoT refers to the network of connected devices exchanging communications. However, we face some challenges in traditional cloud computing where we see increased latency because of the bandwidth limits as well as the far distance between the end devices as well as the centralized servers. Thereby, we propose edge computing as a solution to introduce computational and storage instances near the edge devices. So this is an example of the IoT, which is in a smart homes context. Some examples are shown on how each device in an interconnected network can act as data producers and consumers. However, this will not work well in a traditional cloud-centric network given the mass influx of IoT devices reaching the bandwidth thresholds and therefore resulting in increased latency. So as for the motivation of us adopting edge computing, if you look at this diagram of the traditional cloud computing, everything is being processed on the cloud. So the total time to transport and process on the cloud will take a very long time. Instead, we move most of the processing to the edge nodes and only send the partial tasks to the cloud, and therefore it actually saves a lot more time and helps with controlling the bandwidth and dispersing the data to edge nodes. So if you look at the architecture of the edge computing, we see that there's a terminal layer, which is essentially our IoT devices. We have an edge layer to facilitate the connectivity to and from the terminal layer, as well as data processing and storage. And given the close proximity, we see that the implementation of such a layer actually enhances the real-time performance of devices in the terminal layer with a reduced latency and waiting time. Last but not least, we have the cloud layer, which offers robust computational power and storage capability. This actually serves as an extension to the edge layer to facilitate tasks that the edge layer is unable to perform, as well as storing filtered persistent data in a centralized manner. Here we have some use cases for edge computing. First, we have image recognition. By considering the high volume of users, the inputs are actually processed at the edge layer, abstracting the data into symbolic representations and reducing the irrelevant details, such that we can minimize the data being sent to the cloud and lower the bandwidth usage. Also, for the vehicle-to-vehicle systems, they can be used for accident detection as well as road hazard updates given the connection between different end devices and real-time communication, such that it results in reduced latency. We have some technologies to facilitate the edge computing. Firstly, we have multi-access edge computing. Essentially, it enables a direct interaction with a radio and network resources for ultra-low latency and high bandwidths. It also permits unauthorized services to utilize the edge computing resources in the radio access network. And as you can see at the server, there are some of the services. The ISP can actually leverage on these services to profile consumer data by location, interest, and requirements. And last but not least, it has third-party application hosting, which supports multi-tenancy with access to storage and processing resources, and therefore enabling the IoT services as well as the real-time analytics on the edge nodes. We also have some other paradigms known as fog computing. Essentially, it's a decentralized architecture extending the computation capabilities closer to the edge nodes, and it supports networking and computation on the distributed nodes and enables hardware acceleration. Furthermore, we have cloudlets, which actually have powerful computational instances and storage near the edge devices by offloading heavy tasks. And when transferring a task from the edge device to the cloudlet, is being used on a virtual machine-based approach, where we have two strategies. First, we perform a migration where it transfers the end device states to the cloudlets for seamless processing, as well as a virtual machine overlay where it adds an additional layer to the base virtual machines for smooth operations during task execution. So last but not least, we do see some challenges in the implementation of the edge computing, the most significant one being the data representation as well as abstraction, where different sources have inconsistent data types. So for example, if you filter too much of the detail, it will result in data loss and loss of contextual meaning. However, on the other hand, if you retain too much data, it results in sparse data rows and increased storage complexity. So in this case, some of the good topics to research on would be to adopt adaptive abstraction rules such as flexible data mapping, and also implement a standardized protocol to facilitate a unified data representation. We do have some of the other limitations such as security and privacy and network connectivity and scalability, but in the interest of time, that will be all for my presentation. Thank you.